Math 356 lecture 2. So let us start at the point, common point from yesterday. We said we want to find the Fourier series representation of a function f of x. So in the lecture yesterday, I explained that a Fourier series expansion is something of the type ak cos kx plus bk sin kx. So the question that was posed by Joseph Fourier was whether you can expand any function in the shape of the sum of sines and cosines. And the answer turns out to be yes. The important aspects I also did the voice recording as well, in case you want that separately. But I don't know where it goes to in the phone. I couldn't find the file. Somebody knows, you can show me later. Well, I was saying that, yes, you can write this in terms of sums of sines and cosines. And the main ingredients here are these two guys. How do you find these coefficients? Yesterday, I went into depth of explaining what we mean by inner product spaces. So if you're going to be revising this lecture by yourself, you need to take note of what we call inner product spaces. And brief definition, this bracket FG is defined to be the integral from minus pi to plus pi of f multiplied by g dx. So the inner product is just the integral of the product of the two functions. And if fg is 0, then we say f and g are, what's the word? Orthogonal. It doesn't mean that they are perpendicular in some sense. It's just a word, because inner product carries the same meaning as dot product. So when the dot product is 0, what does that mean? It means that the two functions are perpendicular. I'm sorry, two vectors are perpendicular. Here we are not dealing with vectors. Okay. It didn't happen. I could actually make the lights. Yes. I think you can manage this a little better than yesterday's. All right, let's carry on. So I was saying that yes, we want to write the function in that shape, and then we obtain what is called orthogonality relations. Yes. This thing is unstable here. Orthogonality relations. Now, I'm not going to go into all the details, but yesterday I derived everything from scratch. All of the work was done, from point to point. So there's no need for me to repeat it. So you can watch it. But basically, things like sine kx, sine nx. We discuss things like that. Sometimes it's 0, sometimes it's pi, sometimes it's 2 pi. When the two are different, sine kx, sine nx. Oh, okay, let me just put that in the same place as that. Sine kx, sine nx, cos nx, sorry. Sine kx, cos nx. When these two are different, then we know that this is always going to be 0. And there were many other ones that we derived as well. We needed those because we wanted to try to obtain a formula to find AK and BK. That was the main aim of the game yesterday. How can we find a formula to establish AK and BK? I drew a parallel between Fourier series and ordinary Taylor series. In the Taylor series, it's AK x to the k. And there's no sine and cosine. It's polynomial. However, here, well, in the Taylor series, the AK there is a way to work it out. It's the kth derivative of f divided by k factorial, if you remember that from first year. Okay? So that's a way to get the answer there. How do you do it in this case? Now we established the coefficients, so I'm just going to jot them down for the benefit of those who are not here. You can start from this point. You can follow from yesterday's lecture by reading it or going through the video, but from here, you should be able to follow what's happening. Fourier coefficients. So we found yesterday that A naught is 1 over 2 pi integral from minus pi to plus pi f of x dx. So if I give you any function and ask you to find its Fourier coefficients, the first one, A naught, is simply integrated from minus pi to pi divided by 2 pi, and that's the first number, A naught. All the other k's, AK, are obtained by the formula 1 over pi integral minus pi to plus pi f of x cos kx dx. So these are valid for k equals to 1, 2, 3 onwards. And likewise, bk has the same shape, minus pi to plus pi f of x. This time it's sine kx dx. So these formulas will help you to find those mystery coefficients. What can we say about B0? Unlike A0, you can calculate the integral here. B0, there's no need to do any work, it's 0 by definition, because it's arbitrary. If you have B0 sine 0, what is sine of 0? It's 0. So what difference does it make what number is in front of 0? Anything times 0 will be 0. So B0 can be anything. That's why we said let's call it 0 by definition. All right, so yesterday I was busy with an example. Let me finish the example. We don't have to do the whole example again. Continuation of example 1. To recap, example 1 had the function f of x equals to 1 between minus pi and 0, and it's 2 between 0 and pi. If you draw this function, it's simply two pieces of straight lines, minus pi plus pi. So from here to there, it's number 1. From here to there, it's number 2. Well, it doesn't have to be there. It goes up to pi. So slow. Ooh, uphill. Okay, so it goes up to there. So that's a very simple graph. Two pieces of straight lines. Now I want to know whether you can write that function in terms of cosines and sines. Yes, I know you're thinking, this is so stupid. I mean, it's such a simple thing. Why is he making it more and more complicated? Why do you want to write a number like 1 as a series in terms of sines and cosines? You're just making life much more difficult. It turns out that this is a very important step because in engineering and various other aspects of physics, we need to convert ordinary numbers into sines and cosines. If you can do that, then you'll be able to express or solve a number of differential equations, like the heat equation, Laplace equation, and there's a number of other types of equations that you can solve. But that's a crucial step. But I'll show you some more fascinating stuff, which is totally useless, but quite jaw-dropping anyway. So just hang in there. Now, the first step here in the solution is to calculate A0. A0 is equal to this thing is moved up. The formula is 1 over 2 pi. You just have to hit this into the formula, and you'll get this Windows laptop is just too lazy, unfortunately. Reaction time is too slow. So A0 is 1 over 2 pi integral of f of x dx, and from minus pi to plus pi. In this particular example, it's 1 over 2 pi integral from minus pi up to 0. There's two pieces here. 1 dx plus from 0 to pi, there's another piece, 2 dx. Crank this out, eventually you'll get the answer 3 over 2. Simple calculation. Then if you calculate AK, it's 1 over pi Same kind of calculation, integral from minus pi to plus pi. This time is f of x cos kx dx. Again, you've got two pieces to contend with, so it's 1 over pi. First piece will be integral of 1 cos kx dx from minus pi up to 0, plus integral of 2 cos kx dx from 0 to pi. I think you can see you can't put the two integrals together because it goes to different points, minus pi to 0, 0 to pi. There's different domains, so you can't merge them. Anyhow, you can calculate this, go through the whole motions like we did yesterday, and it turns out that one becomes 0. It turns out that way. Then the part that we were busy with yesterday was the sine part. Did you work it out? I asked you to try, have a go at that. So come around and check who worked it out. Now, as a teacher, you must always believe in your students. Have faith. You know, standing here, that there's no need to go and check. Everyone who was there yesterday has done it. That's the faith that we have, and I commend you for that. 1 over pi integral of f sine kx dx. Feel free to stop me anytime you would like it. And this time it's 1 over pi integral of, same kind of story again, minus pi to 0, 1 sine kx dx, plus integral from 0 to pi, 2 sine kx dx. Now it's a question of just cranking that out. And I don't think the answer turns out to be 0 in this case. Let me just get a darker pen. So this works out to 1 over pi. Okay, what is the integral of sine kx? Integral of sine kx? Yeah. Cos kx or minus cos kx? Minus, be very careful. The signs can stuff you up here. Minus cos kx divided by the derivative of the inner function, which is k, and the limits are minus pi up to 0. Then the next one is plus, here it'll be minus 2 cos kx over k. The limits this time are 0 up to pi. Right, so let's now work this out actually. So this is going to be 1 over pi. Let's substitute the upper limit first. Minus cos 0. What's minus cos 0? Minus 1. Minus 1. Minus 1. And then let's put the minus pi in here. Minus cos of minus pi. Actually, it's k minus pi. Let me just digress a moment here on the side, just to show you a few tricks with cosine and sine. You know that cos of minus theta is cos theta from high school, trigonometry. So if you got cos of minus k pi, it's the same as cos of k pi. Right, so that is going to be used often. Then, what you should realize is that cos of k pi, okay, what's the value of cos of 1 pi? Cos pi, cos of 180 degrees, minus 1. Okay, so it's going to be minus, well, cos of 0 is 1, right? First one is 0. Then it's minus 1. What's cos of 2 pi? 1. What's cos of 3 pi? Minus 1, then 1. So you see it alternates. And what's a nice mathematical tool to encapsulate that behavior? Anyone knows? Minus 1 to the power k. So if you write minus 1 to the power k, whenever k is, well, you see here, k is starting from 1, right? Actually, I should have deleted this one here because A naught is completed. Remember, A naught is finished. We said this is k equals 1, 2, 3. So we don't need the first one. So when k is 1, minus 1 to the power 1 is minus 1. When k is 2, minus 1 squared becomes plus 1. When k is 3, it's minus 1. K is 4. Whenever it's even, it's plus 1. Whenever it's odd, it's minus 1. So that's a neat trick to handle that, right? So now when I plug in this minus pi into here, it'll become cos of minus k pi. See that? And then I can write that as cos k pi. It's the same thing. Sorry, it's minus 1 minus cos k pi all upon k. Now on this side here, let me put brackets here so that we can be very careful about how things work here. Although this is the simplest question we're handling, problem number 1, but you still have to be very careful. So minus 2 into, now let me plug in pi here, cos k pi, right? It'll be cos of k pi on top. Subtract, cos of 0 is 1, all upon k. So as I said, 1 over pi, this is minus 1, and cos k pi is minus 1 to the power k. So it's minus 1 to the power k. Over here it's minus 2 times minus 1 to the power k. And hang on, there's a plus somewhere here. Oh, sorry, this is a plus, eh? Why is this a plus? Why is it a plus? Because it's a negative here. It's minus and you subtract. In the integration, don't you put the first number in, you subtract, and then you put the second number in. So when you put minus 0 in here, it's minus 1. Then it's minus of minus. The same minus here. So be careful with that. To the k, and here is plus 2. Okay? All upon k. Right, let's take it to the next page. Let's simplify all of that. So that's 1 over pi. 2 minus 1 is 1 minus. There's 2 of these and 1 of that, so it's minus 1 over k. 1 to the k, rather. All upon k. See if you're happy with that. If you're not, let's talk about it right now, because this is going to recur. It's going to come about often in the lectures to come. This and this becomes 1. Minus 2 plus 1 becomes minus 1 of that. Now, so that is, what's this? bk. I'm working with bk. Notice now, if k is even, what happens to bk? So if k is even here, minus 1, let's say squared. Minus 1 squared plus 1. 1 minus 1, 0. So can you see this entire thing dies? bk is 0, right? So it becomes like 1 over pi into 1 minus plus 1 over k, and it's going to be 0. Likewise, consider if k is odd, you won't get the same thing happening, but you can simplify this. bk will be 1 over, I can put this as k pi now. Put the k in the front, take this k out here, k pi, 1 over k pi. And in the bracket we will have 1, yes? 1 plus 1, it'll be 2. Good. 1 plus 1, that'll become 2 over k pi. So there we go. We now worked out the coefficients of AK, BK, A naught, B naught. We don't need B naught. We know it's 0. So what is our achievement so far? We have now said, so the function f of x, which we know is 1 for minus pi up to 0, and 2 from 0 to pi. This is the same as 3 over 2, that's A naught. A naught was 3 over 2, if you remember. Plus, now you should have AK cos kx plus BK sin kx. But remember, AK became 0. Only the sine part is alive here. This problem, go back and see on the top. So you'll have sigma 2 over k pi that is now AK, sine kx, bk, sorry. And this is valid when k is odd. When it's even, it's 0. So that's now the Fourier series for this function here. The Fourier series representing this function is exactly that. Okay, customarily we can write this as 3 over 2 plus, we can pull the 2 over pi outside, sigma, sine kx over k. K equals odd. You can't take the k outside, right? Because the k is odd. It must behave according to k equals odd when you do this sigma. When you sum it, you add k equals to 0, k equals to 1, 2, 3, 4, 5. All right, so that is the Fourier series. In other words, if I expand it, let's see what this means. If I expand it, it's like saying that this is 3 over 2 plus 2 over pi, and let's take k equals to 1, the first odd number. So it'll be sine 1x over 1 plus k equals to, what's the next odd number? 3, sine 3x over 3 plus sine 5x over 5 plus sine 7x over 7, and so on. Believe it or not, if you have to draw a graph of that function, it will actually approximate this function. You believe it? Let's show you. I'll just turn down this Mathematica. Okay, so by the way, Mathematica is freely available for all students to download, so you should download it. The university pays quite a lot of money for the site license, so you guys are entitled to use it. And you should. You won't use it a lot, but certainly for calculations, makes life very easy. So I want to plot the function. You have to learn the syntax here, right? 3 over 2 plus, what is that, 2 over pi? Pi for pi, times, what is the first one, sine x. Okay, let me just stop there. This should be thoroughly unconvincing because this is only one thing, right? Let me take it from minus pi to pi. Plot range specification. Oh, something wrong here. Oh, x is missing here. X. So that's the so-called function representing y equals to 1 and y equals to 2. Is it okay? I don't think anyone can be convinced that that is y equals to 1 and y equals to 2, right? But see what happens as I increase the number of these terms here. If I add, what's the next one? Sine 3x over 3. 3x over 3. All right, let's see what happens now. See what's happening. Check out the wave. The lights are so poor there. The wave is there. And then let me go further. What's the next one? Sine 5x over 5. Sine 5x over 5. Check that. Let me go crazy now and do quite a few at one time. Let me put sine 7x over 7 over 7 plus sine 9x over 9 plus sine 11x over 11. Okay, let's see. Can you see what's happening? You observe how these ripples are gathering in the right place. Let's see if I can make this bigger. Can you see that? Look at this here. Can you see how this is gathering near 1? By the way, this is 1. This is not the x-axis. X-axis is 1 below it. Mathematica has behavior of putting the x-axis close to the graph. I mean, an axis close to the graph. This is actually y equals 1. That's y equal to 2. But can you see what's happening here? As I take more and more terms, can you see how this ripple is becoming a better approximation to 1? It's getting closer. And this is an infinite series, by the way. I only did terms up to 6. If I have to go on to infinity, these ripples will become indistinguishable from 1. It will be exactly on 1. It will converge to 1 here, and it will converge to 2 here. Isn't that spectacular? Who would have thought you could actually have a cubic series and you can approximate 2 numbers? It's quite a spectacular happening. I hope you can see that. Some of our students don't see how spectacular the work can be. All right, so it's still recording. Fine. So that should be fairly convincing. Yeah, now one more thing. Okay, so you may not like that. So this is 1 and 2. Eh? Now, let's try to get what we shall call some results. Some interesting accidental results. We don't set out to actually find these results, but they happen to appear in front of our eyes, and then we get wowed by, actually this is so useful. So, plug in x equals to say pi over 2. Well, note, what is f of pi over 2? Remember the graph is like this. From minus pi to 0 is y equals to 1. From 0 to pi, it's y equals to 2. So I am asking the question, what is the y value when x is pi over 2? Here. When x is pi over 2, what's the y value? 2. So the y value is 2. Right, now let me milk that for something. So the left-hand side will be 2. The right-hand side is 3 over 2 plus 2 over pi into. Remember I said put x equals to pi over 2. It will be sine pi over 2 plus sine of 3 pi over 2 all over 3 plus sine of 5 pi over 2 all over 5 plus sine of 7 pi over 2 all over 7 plus blah 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 up to infinity. Let's now try to compute. Okay, let's take the 3 over 2 across. 2 minus 1.5 is half. Half equals to 2 over pi into. What's sine of pi over 2? Sine of 90. Sine of 90. 1. What's sine of 3 pi over 2? In other words, 270. Sine 270. Minus 1. So it's minus 1 and it's over 3, right? What is sine of 5 pi over 2? So you go another, like at pi over 2, you go another 2 pi around. That comes back to 1. So, but this time it will be 1 over 5. The next one will be minus 1 over 7. The next one will be 1/9. Then minus 1 over 11. And so on and so on. So if you look at that, what is jumping out at us there? Anything you can observe? Well, let's cross multiply with pi over 2. So I can get pi over 4 is equal to 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 minus 1/11 and so on. Or I can say pi equals 4 times 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9, etc. What have I achieved now? I found a way to find the value of pi. And this is quite an important thing to have. It's an irrational number. It's an irrational number. It's not just an irrational number. In fact, it's a transcendental number. It's on a higher level than root 2, for example. Root 2 is an irrational number also. But root 2 can be constructed. If I have a square with size 1 and 1, the hypotenuse will be root 2. I can construct the number root 2. But can you construct the number 5? Can you construct a length of 3,141,592 up to carries on? Let's give you distributions. You can't. It can be proven. In fact, if you do advanced mathematics, if you do the honors course in algebra, you teach them that why you can't construct pi. It's a beautiful theorem, but it's more advanced than what you guys are exposed to here. It needs a theory of extension fields, and the theory was established by the great French mathematician Évariste Galois, who obtained his PhD at the age of 21 from the French Polytechnique, and soon thereafter, next year, he died. Tragic story. It's true. You can read about it. Turns out there was something to do with a girl, and he challenged another guy to a duel, and he lost. You know what is a duel? Those days they were stupid. He challenged someone to a duel, and that's how he died. By the way, even Archimedes, the way Archimedes died is also quite freaky. Archimedes was drawing his geometric patterns on the sand somewhere in Greece, and then a Roman soldier came there and asked him to stop. He didn't ask him to stop. He stood next to him, and he said to the guy, "You're standing in the way, I can't see it. Shadow is coming onto my drawings." And they had a bit of a fight. The Roman soldier threw his sword and killed Archimedes. These are true stories. I'm not making them up. This is not like a soap opera that you guys watch at 6 o'clock in the evening. Okay, so that's the spectacular derivation of a value of pi. By the way, there are many formulas obtained in the history to find pi. Some of them are due to Vieta, early calculations of pi. Ramanujan, the great Indian mathematician, there's a movie about him. He calculated pi. His formula has a very quick convergence rate. And you may find that that's really the formula programmed into many calculators because it converges fast. You don't want a sequence. Like this one here converges slowly. This one converges very slowly. It converges, but very slowly. You need lots of terms to get high degree of precision. You see, because you can, these numbers are quite close to each other. Any questions? So, yes? What is that? Oh, I imagined the question. Okay. I have to make my own questions here. You guys don't ask anything. Really. I have to generate my own enthusiasm. Yes, I think what you're wondering about now, and I'm sure this is running through your mind, let me settle this immediately. What about convergence? How do you know whether this function actually converges to the Fourier series converges to the function? How do you know that? It's a bit of a complicated business. We haven't got the space in this course to actually go into details. But the great mathematician Dirichlet found conditions under which functions will converge, and they turn out to be quite simple. I'll just enumerate them for you. You can just jot them down. So there's no need to go into details discussing them. So if f is piecewise continuous, and most functions are, and monotonic. Monotonic means it's either always going up in that piece or always going down in that piece. Now, monotonic means its derivative is positive or negative, not both. Unlike a parabola, it's not monotonic. The parabola is monotonic from 0 up to infinity and from minus infinity to 0. But from minus infinity to plus infinity is not monotonic. What was the thing? Yes. Then I'll use F series. I'll use the F word here. F series converges to f of x. Okay, the second point is at the jump discontinuity. Discontinuity. I'm battling here with this laptop. At the jump continuity, it converges to the midpoints of the jump. And at the endpoints, at the ends, the F series converges to, it's actually f of pi plus on the right, on the left, sorry, pi plus on the left, and f of pi minus on the right. And in fact, the average of that. Details are not required. What time do we finish? Plus y. What? Ah, yes. It's a long time since a student spoke the truth. Okay, guys. So let us end off now with this problem. It's a very short problem. You're still writing that. I want to discuss the example 4 in the book. Example 4. So I firstly dealt with the function y equals to 1, y equals to 2. Those two simple straight lines. Now let me take a function f of x equals to x. Slightly harder function, but it's the straight line y equals to x and confined between minus pi to pi. Right? So if you want to see a picture of it, so from minus pi to plus pi, is that line there. Can I write a Fourier series representing the function y equals x? That's the question here. So let's crank this out. Don't get too worried. I'll leave some stuff for you to do yourself. You may be getting upset there. Why is he doing the whole problem for us? Does he not know that we want to do it ourselves? I understand. I get you. I hear you. You're speaking very vocally. So, A naught. You see, now those guys who were absent yesterday may also have missed some of these thoughts here. A naught, the formula is 1 over 2 pi integral minus pi to plus pi f dx. Okay? And in this example, it's only one piece here. So it's x dx from minus pi to plus pi. Now, if you were following yesterday, you may be able to write down the answer immediately. If you are not following yesterday, you can do the integration of x. What is the integral of x? X squared over 2. Substitute the pi and the minus pi and calculate it. What will the answer turn out to be? 0. So what's the simple argument for that? Did I write 0 already? Oh, I gave you the answer. I'm helping you more than this. Anyway, so what's the argument why it's 0? Yes? It's an odd function. Yes, very good. This is an odd function. You can see it's odd. It has symmetry across the origin 0, 0. So it's an odd function. F of minus x equals to minus f of x. Let's see if we can score a little more using similar thinking. Sorry, I want to get AK next. AK. AK. That's 1 over pi integral minus pi to plus pi f of x cos kx dx. In other words, that's 1 over pi integral x cos kx dx minus pi plus pi. By the way, when you say odd and even functions, you must have the same limits here, minus and plus, the same numbers. It has to be from the same number on the left to the same number on the right. In this case, what's the answer there? Is it 0 again? We know x is odd. What about cos kx? It's even. Odd times even? Odd. So this is going to be effectively odd. If that's odd, that's even. Odd times even equals to odd. So it's 0. Integral of an odd function is always 0 from minus a to plus a. So we scored there. Two things. Now, you see, if you don't know that quickly, what will you do? You will hit this with integration by parts. You will knock this with integration by parts, and then you'll get frustrated because at the end of the game it will be 0. But you should have known that up front. That's the point I was making yesterday. If you can realize things quicker, it'll save you a lot of trouble. You won't have the same joy here now with BK. This time it's 1 over pi integral minus pi plus pi f sine kx dx. 1 over pi integral minus pi to plus pi x sine kx dx. This time it's odd times odd, which is even. Remember, for those who were not here yesterday, these are not numbers, these are functions. When I say odd times odd, I'm not saying an odd number times an odd number. I'm saying an odd function times an odd function. That's even. Okay? So now you got no, this is now even. So there's, all you can do, you can actually do something. There is some value. I said you can go from 0 to pi of x sine kx. This helps. And you can double the front because it's symmetrical. It's symmetrical. What you see on this side, you see on that side. So you can double. You can go from 0 to a and double it. That's just a mathematical thing. Now you have to actually crank this out. So here you've got to hit this with integration by parts. So you can say let that be u and let this be dv. So let u equals to x, then du will be equal to dx. Let dv be sine kx dx. Now we want v, you have to integrate this. Integral of sine is minus cos kx over k. So, okay, time has beaten us, but now you must calculate this. I'm leaving this for you to do at home. uv minus integral v du.